So we need to review and discuss what we know about quadratic functions and how we graph them. So I'm going to share some explanation and some reminders to you. And if you notice, we're going to look at the two different types of equations that you might see, and how we will use those in order to help us with the graphing. But first, just some reminders of things that we know about quadratic functions and then their corresponding graphs, which we know are parabolas. So we know we're going to be graphing parabolas. So if you think about what we know about parabolas and the shape of those graphs, we know that depending on what the value is for our A, our value out front, depending on A, the graph either opens up or down. Down, I'm trying to write fast, which in turn means, if you think about it, that means that we either have a maximum value or a minimum value. Let's think about what else we know. We know that there's going to be a vertex, and in one of these forms of the equation, the vertex is very easy to find, and the other not so much, but we'll talk about how we do find it. We know there is symmetry in the graph, and along with that symmetry, we know we talk about the axis of symmetry, right? And along with that line of symmetry, we know the equation will be of the form. So EQN, to abbreviate equation, is of the form for the line x is equal to whatever that number is. And that number is the x coordinate for our vertex. So it's actually, I put number there, a number sign there, but actually it's x equals h, isn't it? So we're going to talk about what h stands for here in just a second. All right, so onward, let's talk about a few other things here. The quadratic function, if you notice in this particular form, is what's referred to, it said standard form there, but that's actually vertex form. So fix that for me, please. So that's vertex form. And we know that the vertex, or the point that is given, is going to be of the form HK. And we know that, as I mentioned up there, that this parabola is symmetric with respect to the line x equals h. And then also we know that if the A value out front, if the A value is positive, then we know that the parabola opens up. And if the A value is less than 0, that means it's negative. That means that the parabola opens down. Okay, so we need to talk about and refresh our memory on the process of graphing if we are given the equation of a parabola, a quadratic, in vertex form. And then this is what's referred to as standard form, the ax squared plus bx plus c. So we're going to talk about and kind of work through the steps for how we solve each of these different types of problems. So if you notice, it says determine whether the parabola opens up or down. We want to figure out what the vertex is, and that's easy enough to do from our HK. We want to find x-intercepts, and we want to find y-intercepts, and then we graph those points. And yeah, we use symmetry in order to graph some of these points, and then we connect them with a smooth curve. So we'll look at that in just a second. The other method, as you know, this is a little bit more involved, but we've done this already also. So if you see standard form, this ax squared plus bx plus c, Remember, to find the vertex, we're going to do opposite of b over 2a. And then what this notation means is that we plug in that value that we find and we get the corresponding y. So that helps us find our vertex. And then from there, we're going to use other points. We're going to basically do a table of values to find more points and use symmetry to graph. So let's look at some examples of how this is done. So we're going to look at the easier of the two first. So we are going to look at this vertex form. And we know from all of our transformations a lot of information about the graph, don't we? So we know our vertex is at the point 1, 4. So that tells us that we know that our axis of symmetry, and I'm going to abbreviate that AOS, is the line x is equal to 1, because it's the x value. And we need to figure out what our x and y intercepts are. So let's go ahead and graph the point 1, 4. 1, 2, 3, 4. So we know it's going to open down. We could make a note about that as well, because the a value, if you notice this negative sign out front. So we're shifting right 1, we're going up 4, and we're opening down. But we need to kind of figure out exactly where the point is, where the graph is crossing the x-axis and the y-axis. So let's do that. So that's what it's saying, is find the x-intercepts by solving for setting that equal to 0 and then computing when x is equal to 0 and when y is equal to 0. Sorry, got distracted there. All right, if we plug in, if we set y equal to 0, then we get 0 is equal to negative x minus 1 quantity squared plus 4. So if we solve here, then we subtract 4 from both sides. And we can divide by this negative 1. And so we get that 4 is equal to x minus 1 quantity squared. Now, if we take the square root of both sides in order to solve, and we've talked about this just recently, if we take the square root of both sides in order to solve, then we know we have a positive or negative 2 that we have to consider for the square root. And so then if we add 1 to both sides, we get that x is equal to 1 plus or minus 2. So that tells us that x is equal to 1 plus 2, which is 3. And we also get that x is equal to 1 minus 2, which gives us negative 1. So that gives us points at 3, 0, 1, 2, 3, 0, and then also at negative 1, 0. We also, if we plug in x equals 0, then we get the opposite of negative 1 squared plus 4, and this is if we plug x equals 0. So we square negative 1, we get 1, and then that still makes it negative with that 1 out front. So we get 4 minus 1 is 3. So that's telling us that we have that point, and using symmetry, that means we also have this point, because that's our y-intercept, and we have got a nice graph there. So if you notice, we are being more specific now with showing specific points rather than just doing a rough sketch of the graph. Okay? All right, let's take a look at this second one. This one is a little bit more involved because this is in standard form. So if you recall, if we have equation in standard form, then we find the opposite of b over 2a. And so the opposite of b is going to be negative 4 over 2 times negative 1. So we get negative 4 over negative 2, which is positive 2. So that tells us that we know our vertex is at 2, something, and we have to figure out what that something is. So we're going to plug 2 back into that equation. So we get negative 2 squared plus 4 times 2 plus 1. So we get negative 4 plus 8 plus 1. So what does that give us? 4 plus 1, which gives us 5. So that's telling us that our vertex is at 2, 5. So 1, 2, 1, 2, 3, 4, 5. We can plot that point. We know this is a parabola that is opening down. And so we can plug in x equals 0. And if we plug in x equals 0, then all of this disappears. And we just have the point 0, 1. And using symmetry, then we know we have that point as well. We also need to find where it's crossing the x-axis. And actually, in this case, it is not crossing at any nice pretty points. So we do have to do, it's not going to factor, so we have to do quadratic formula. So opposite of b plus or minus the square root of b squared minus 4ac all over 2a, which will give us a negative 2. So we get negative 4 plus or minus the square root of, that gives us 16 plus 4, so we get the square root of 20 all over negative 2. Now we need to clean this up. This gives us negative 4 plus or minus 2 root 5 over negative 2. And we need to think about Mickey Mouse ears here. So we have a common factor. And in this case, just to make things look a little bit nicer up front, we're going to divide by negative 2. So we end up with, a positive 2 plus or minus the square root of 5 all over 1, basically. So 2 points that we have, the x-intercepts that we have are 2 plus the square root of 5, comma, 0, and 2 minus the square root of 5, comma, 0. Now you can plug those points into a calculator and actually figure out approximately where they are. But it ends up being about right here and about right here when you look at where those points are, what the values are for as a decimal. And then we get the basic shape of that graph. With a few points in there just to kind of help get a good visual of what it looks like. I wanted to point out real quickly before we move to the back page, which is pretty straightforward and easy. I wanted to show one other example just to kind of help you with this process. If you notice, this equation is in standard form. It's like the ax squared plus bx plus c. But there's no b term. There's no b value. You're going to see an example, at least one example on your worksheet where you're going to practice with this, where this is the case. So I wanted to kind of point that out to you. So if you notice, it's in standard form, there's no b value, and I want you to think about what that means. It means that our b value is equal to 0. And so then to figure out where our vertex is, I want you to think about the fact that what that means is that you're not going to shift left or right at all. So the vertex will be right on the y-axis somewhere. On the y-axis. So in this case, if you plug in 0, you're going to find that the vertex will be at the point 0, 2. Okay? So keep that in mind. Think about that as you are working on the worksheet. All right, onward. 2 more examples. The last one's just kind of an interesting, oh, by the way type thing that I want you to notice. So the next type of problem that we're going to look at and talk about, if you notice, it says, consider this quadratic function. Without graphing, determine if the function has a maximum or minimum value, and then find that value. So the wording here, find the value, we're going to talk about what that specifically means here in just a second. So to decide if it's a minimum or a maximum, we need to decide whether this particular function is opening up or down. And the a value, because it's greater than 1, greater than 0. It's positive. So that means we know that the parabola opens up. So that means it would look something like this. And if you think about what that means with respect to the vertex, that means that we have a minimum. Now to find that minimum value, and they just want the value of that minimum value, it's kind of a two-step process. We're going to do opposite of b over 2a first. And in this case, the opposite of b would be 16 over 2 times 4. So we get 16 over 8, which is 2. So that's our x-coordinate. But to find the value of what our minimum value is for this, we're going to plug that 2 in. So we're actually finding the y-coordinate, and that's what our value is. And we just want to state the y-coordinate. We're not going to write it as a coordinate point. It's just the y value. So if we plug 2 back into this, we're doing 4 times 2 squared minus 16 times 2 plus 1,000. And if we do the math here, we get 16 minus 32 plus 1,000. And so we get 984. So the value, the minimum value here is 984. Yes, our vertex, this also tells us that we know what our vertex is for this graph, that it would be at the point 2, 984. But I want you to remember that if it just asks for the value, we're just going to give the y-coordinate. For the second example here, if you notice, this parabola has an a value that is less than 0, so that means it opens down. So that means that our vertex, would be at the highest point, so it's a maximum value. So once again, we're going to do our opposite of b over 2a. So we do negative 48 over 2 times negative 16. And this one's not so pretty. We get 1.5. We get a decimal or a fraction, whichever way you want to think about that. So we're going to plug that value back in. So negative 16 times 1.5 squared plus 48 times 1.5 plus 1296. Yes, hopefully you're noticing we can get some pretty big numbers here. And this maximum value in this case is 1332. So there's our maximum value. All right, one last problem here, and this is just kind of a neat, kind of an application type problem. So it says you have 120 feet of fencing to enclose a rectangular region. So all together, if you think about it, that's our perimeter. So 2x plus 2y has to be equal to 120. Find the dimensions of the rectangle that maximize the enclosed area, and what is the maximum area? So first order of business is to solve for y. So if we subtract the 2x from both sides, we get that 2y is equal to 120 minus 2x, and then we're going to divide by 2, and so we get 60 minus x. So that's what y is equal to. Now, it's talking about the area. So this was the formula for perimeter. Now we need to look at our area formula. We know to find our area, we're just going to multiply x times y. Only in this case, we want to think of our y value in terms of x. That's what I was doing here, is rewriting that y value in terms of x, so that we get an equation with just the one variable. So if you notice, we get 60x minus x squared, or to kind of like write this like in standard form like we are used to seeing, if you want to write that as negative x squared plus 60x, that might be helpful. Now, in order to answer this question, we we've just got to do our opposite of b over 2a. So we're going to figure out what that x-coordinate is for our vertex, what that would be. So we're going to do opposite of b over 2a. And in that case, we get negative 60 over negative 2, which gives us 30. Now, this particular value, we can go back and plug back in. And if we do that, we find that our area, our maximized area, is going to be 30 for x. And if you think about what y would be, we'd do 60 minus 30. So we also get 30. So our maximized area is 900 feet squared. So that was just an example of an application type problem that you may see, given quadratics. All right, work on that worksheet with the graphing, and we will talk about that tomorrow.